In this lesson, we will explore and relax some of the OLS assumptions. We've already identified some variables as potential regressors. The categorical ones will be included as dummies, so we don't need to worry about them when checking the assumptions. The continuous variables, price, year, engine volume, and mileage, are those that are likely to be more challenging, cause us more problems. Let's check for linearity using a scatter plot. These are the three scatter plots that we obtained. One for price and mileage, one for price and year, and one for price and engine volume. We can spot patterns, but definitely not linear ones. We know we should not run a linear regression in this case. We should first transform one or more variables. Recall the distribution plot of price, too. All these plots are pointing us towards the idea that price is not normally distributed, and from there, its relationships with the other rather normally distributed features is not linear. The patterns are quite exponential. As I have told you before, log transformation is a common way to deal with this issue. It is especially useful when facing exponential scatter plots like we do now. Let's take the log of price and create the plots again. NumPy has a method which calculates the natural log. It is np.log, and in brackets what we want to find the log of. Let's declare a variable called logPrice equal to np.log of data price. Next, we will just add it as a new column at the end of the data frame, which for us will be logPrice equals, well, the logPrice variable. All right, time to plot them again. We can see a linear pattern in all plots now. The lines fit the data so much better. Superb! At this point, let's drop the original price variable from the data frame since it is no longer needed. Next, we usually deal with the no endogeneity assumption. There are tests to check if it is violated, or one can take the residuals and find their correlation with each independent x. I can tell you that the assumption is not violated, so it is of no interest. Moreover, we will have the opportunity to discuss them after the regression is created. The third assumption had several parts. Normality is assumed for a big sample, following the central limit theorem. The zero mean of the distribution of errors is accomplished through the inclusion of the intercept in the regression, which we discussed already. Finally, the homoscedasticity assumption generally holds, as we can see in the graphs. The reason for that is that we already implemented a log transformation, which is the most common fix for heteroscedasticity. The fourth assumption is no autocorrelation. We don't really need to put much effort into that. The observations we have are not coming from time series data or panel data. They are simply a snapshot of the current situation at a second-hand car sales website. Each row comes from a different customer who is willing to sell their car through the platform. Logically, there is no reason for the observations to be dependent on each other. We are safe. Finally, we should check for multicollinearity. It is logical that year and mileage are going to be correlated, right? The newer the car, the lower its mileage. Therefore, we have grounds to expect some degree of multicollinearity in the data. Unfortunately, sklearn does not have a dedicated method to check this assumption. We must turn to our old friend, stats models. One of the best ways to check for multicollinearity is through VIF, or variance inflation factor. VIF produces a measure which estimates how much larger the square root of the standard error of an estimate is, compared to a situation where the variable was completely uncorrelated with the other predictors. In order to save time, I will simply copy-paste the relevant code and quickly go through it. First, we import the VIF method from stats models. Next, we define the features we want to check for multicollinearity. Currently, we have only 3 continuous variables: mileage, engine volume, and year. What's left are categorical variables that we haven't dealt with yet. Therefore, let's simply take those 3 and evaluate their intercorrelation. The rest is syntax. Please make sure you check the article after this lesson, where we provide supplemental resources about this measure. Okay, let's focus on the resulting variance inflation factors. When VIF is 1, it means that there is no multicollinearity at all. This is also the minimum value of the measure. Generally, values between 1 and 5 are considered perfectly okay. Here's where it becomes tricky. Some sources state that a VIF above 5 is unacceptable. Others put the boundary at 6. I've also often seen 10 as the cutoff line. Unfortunately, there is no firm consensus on the topic. From my experience, you'd rarely find data so perfect that all features have a VIF below 5, so that is somewhat conservative. For our example, it seems like year is definitely too correlated with the other variables. Therefore, I will only remove year. Let's declare data no multicollinearity equal to data cleaned drop year on axis 1. Alright, in the next lesson, we will pre-process our categorical data and run the regression. Thanks for watching.